Section 8.2, properties of exponential functions. We're going to identify the role of the constants in y equals ab to the cx power and to use e as a base. In the previous section, we looked at graphs of the form of y equals ab to the x where a is greater than 0. For example, we're going to graph the function y equals 3 times 2 to the x power and make a t-chart of values to do so. If it helps, put parentheses there. So usually what I do, it's pretty easy to plug in the values for x and y. If you want to, you can plug them into your calculator, plug this into your y equals. Notice I put this value in parentheses to the x power, and then go to your table, and I pick positive and negative points. So I'm going to do -2 to 2 for my values. So I'm going to write those down here. And on my table over here, for my y values, I'm going to go by 2s. So I'm going to use this as 10, and that means this would be 20. And I'm going to count on my x-axis by 1s. So this would be 5, and this would be 10. So for this, I have 0, 3. Remember, we counted by 2s, so 3 would be right here. And then I have the points -1, 1.5, which would be here, and this one would be here. And at the value of 1, we have 6, so 2, 4, 6 would be right there. And at 2, we have 12. So my graph looks something like this. And remember, you can check your graph on your calculator. Remember, these values get very, very close to 0, but they don't actually ever hit 0, and we don't cross over that horizontal asymptote that we have. So you can even confirm it by looking at your graph. So here's my graph. Notice it looks like it stops there, but if you even hit trace, notice it's going to keep on going. So don't just stop your graph there. Your graph keeps going. It's just hard to see because it's so close to the x-axis that we have. So don't forget to also draw in your horizontal asymptote, which would be right here. Remember, I abbreviate horizontal asymptote as HA, so it would be the line y equals 0. So that's our graph, and remember we talked about this before, where this is exponential growth, because as you go from left to right in your graph, notice your y values are increasing in value. Since they're increasing in value, that's how we know it's growth. So the next question says, what do you think will happen if a is less than 0? So let's go ahead and graph y equals -3 times 2 to the x power on the same coordinate. So let's do y equals -3 times 2 to the x. And so let's go ahead and use our table to do that. So in my calculator, I put the negative in front, and then I hit graph. Notice now my graph is going downward. So remember we said we had the negative in front, it reflects your graph over the x-axis. And if you go to your table and look at your values that we had before, so notice that we have -2, -0.75, -1, -1.5. So all of these values that we had for y previously are going to be negative. So we have -2, -2.75, and -1, -1.5, 0, -3, 1, -6, and 2, -12. So if we go over here, we're just going to graph the reflection of this graph. So again, the y scale is going by 2s. So we have 0, -3, which would be here, 1, -1.5, and then 1, 6, and then 2, -12. So my graph, remember, comes very, very close to that, and it's going downwards. So my horizontal asymptote hasn't changed. It's still y equals 0. Notice that instead of my, as I go from left to right in my graph, instead of being exponential growth, notice my values of y are decreasing at a rapid pace. So we call this exponential decay. Now be careful when you're doing these equations to always watch out to see if you have a negative in front, because remember before we said we looked at this b value to tell us if it was exponential growth or decay, and since it was above 1 we said it was growth. But you don't want to make that mistake because here your b value is equal to 2, but if you say this is exponential growth, you would be wrong because notice that the negative right here reflects our graph over the x-axis. You have to be very careful to watch out for that. So this reflects graph over the x-axis. Okay. So let's talk about some stuff that we've done during the course of the year. We studied many different functions and their translation. So remember, if we have y equals mx plus b, this was a linear function. And we didn't really do any translations with this. Instead, if this is y equals mx, y equals mx plus b was really the translations, and that's what we graphed. For number 2, this is the absolute value function. And remember the translations were y equals the absolute value of x minus h plus k. For the next one, this was the square root function. And the translations for this were y equals the square root of x minus h underneath the radical and then plus k on the outside. Then we had with the square, that means we have quadratic function, and the shape it makes, remember, is parabola. So for this, the quadratic function, we had y equals x minus h quantity squared plus k. Then the next one, this right here, x and y are being squared and equals r squared. This is an equation of circle. And for the circle, our translation was x minus h squared plus y minus k squared equals r squared. And the last one is the new stuff that we've been doing, which are exponential functions. And so for this one, if you think about all the other problems we did, notice that the h is always attached to x and the y value is always going with the k. So if we even look at this, so like this vertex right here, if I had y equals mx, would go through 0, 0. And it's not really a vertex, sorry, I should just say the graph goes through 0, 0. This would have a vertex at 0, 0. This graph right here starts at 0, 0. This graph also starts at 0, 0. Same thing with this one. This one, however, does not start at 0, 0 because if you have x is 0, anything to 0 power is 1. So really it's 0, comma 1 that we normally go with. For these values, if we have an exponential, then to do the h and the k, it's going to be y equals a times b to the x minus h power and then plus k on the outside. And just like all the other times that we had this, the h value is going to move your graph left and right, depending on if it's positive or negative, and the k value moves your graph up or down. And so just to look really quickly, if I had y equals 2 times 3 to the x minus 3 plus 4, now from my parent graph, we've moved it to the right 3 and up 4 units because this is my h and this is my k. So if instead I had the equation y equals 2 times 3 to the x plus 3 minus 4, this would move my equation to the left 3 and then down 4. So you always want to do the opposite of what you have for your h value, and your k value stays the same, just like we did in a lot of the other equations that we had. All right, so let's go ahead and do some graphs. So we're going to graph y equals 6 times 1/2 to the x power. And we've done this before, so if you wanted to in your calculator, you can just make a table. So I'm going to skip that part. So we have -2, 24, -1, 12, 1, 3, and 2, 1.5. So we're going to go ahead and graph this. So I'm going to go by 2's on my y scale. So this would be 10, and this would be 20, and 1's on my x scale. So this would be 5, and this would be 10. So for this graph, I have the point 0, so 0, 6, which would be right here. And then I have the point 1, 3, and I have the point 2, 1.5, and then negative 1, 12, and negative 2, 24, which would be all the way up here. So here's my graph. And remember, this is a b value is equal to 1/2, so this doesn't have a negative in front, so it's exponential decay, because as you move from left to right in your graph, your y values are decreasing. And if you look right here, our y values are coming very close to 0, so we have a horizontal asymptote of y equals 0. Now, let's look at the next graph that we have. We're going to graph y equals 6 times 1/2 to the x minus 3 power minus 2. So in this case, my h value is 3, my k value is negative 2, because remember the formula is always y equals a times b to the x minus h and then plus k. So you always want to do the opposite of that h value. So that means for this, we are going to be moving our graph to the right 3, and down 2. So you can make a table of values if you want, or you can just count right 3 down 2 from the graph we graphed before. I'm going to go ahead and do this graph in green. Actually, let's do it in green. So I'm going to count right 3, 1, 2, 3, down 2. Remember, we're going by 2's for our y scale. So right 1, 2, 3, down 1, 2. Right 1, 2, 3, down 2. And so, oops. So my graph would go something like this. And for this graph that we have now, if I moved it down 2, that changes my horizontal asymptote. So if it was at y equals 0, now my horizontal asymptote's at right here, y equals negative 2. So we actually moved everything down. So the horizontal asymptote is y equals, it's a line, negative 2. So basically, whatever this number is on the outside, that's going to correspond to your horizontal asymptote. So for the graph above, really it's plus 0, so that's why our horizontal asymptote is y equals 0. So that's nice that it helps us figure out our horizontal asymptote. So let's look at this in our graphing calculator. So I plugged it into my graphing calculator. If it helps, if you have one of those older calculators, you're going to want to put parentheses around the x minus 3. So that might be a good habit to do. If you have a newer calculator, you don't have to worry about that. So for this, if I hit graph, notice that it looks like my graph over here. You could also go to the table values if you wanted to plot those values that we have. So that might be a good idea to do if you get stuck. And even if you go to the graph, notice if I hit trace, my graph is decreasing as I'm getting larger and larger values of x, so we know it's exponential decay still because we didn't reflect it over the x-axis. And if you want to confirm your horizontal asymptote, notice that as I keep getting larger and larger values of x, my y values right here are approaching negative 2, and it looks like a straight line right there because no matter how large of x value I get, I'm never going to be able to reach 2 nor cross over that value of 2. That's why we have a horizontal asymptote there. So again, you can also confirm that by looking at your graphing calculator, or again, it's a number on the outside. So then for the next example that we have, it says we want to, given y equals 6 times 2/3 to the x plus 4 plus 2, describe the translation from the parent graph. So your h in this case is minus 4, because we always do the opposite of h, and then your k value is 2. So for this, my parent graph would be y equals 6 times 2/3 to the x. So how did our graph move? It moved from our parent graph, it moved to the left 4 and up 2. And you can also confirm that by graphing it in your graphing calculator.